Swayam Prabha. Digital India. Educated India.
So this reverse bias voltage will add on to the built-in potential at the interface, and we would see the barrier. Originally the barrier was V0. On top of that we have added reverse bias potential. So by putting the PN junction in reverse bias, we have increased the built-in potential. We have added on top of the built-in potential V0 plus VR, and what this would do is your I diffusion current will reduced substantially, almost to zero. Okay, because we don't have any excess carriers or the concentration of holes on the p type and electrons in the n type, because they all will get sucked into the battery. Okay, because we are applying negative potential to the p type and positive potential to the n type. So as a result of which the diffusion current will drop down to zero. However, this thermally generated minority carriers, they're still there in that region and they will continue to flow. So what we expect to happen is the following. We will have very small diffusion current, and our original drift current will continue to flow in this direction. Okay. As I said again, the I drift is minority carriers and they are moving around under E field, electric field. If you look at this carefully, the only current you can say which is flowing in this direction will be I drift. Okay, so we can write I reverse bias is equal to I drift. Now this is still not that interesting because there is no current flowing, and the current which is flowing in the reverse bias case is again really small. Okay, so now we will go to the most interesting use of the diode, which would be PN junction under forward bias. In this particular case, something very interesting happens. So we take the PN junction and here we are going to connect. This is P type and this is N type. So in this case we are going to connect P type to positive and N type to negative. Positive and negative. Okay. So by connecting positive terminal, we are flooding the P type with positive charges, and by connecting the negative terminal, we are flooding the N type with negative charges. You can imagine a battery as positive charges and negative charges separated, and that gives you the potential difference. Okay. All right. So what will happen then? Now I am flooding the positive charges in the P type, and I have flooded the electrons in the N type. Obviously, we are making P type have lot more holes, and N type we are going to make, we are going to add more electrons. So you can immediately think that, hey, my diffusion should increase. The diffusion current should increase, right? So you will see there will be a large diffusion current. I'm going to show it here on the top. That should flow I diffusion from P to N. The holes will flow from P to N type, and then they will get replenished again, flow this way, and as a result of which you will see a current flow across the junction. The width of the depletion region will reduce substantially. Okay, so you will see really small region here which will have depletion region. So this would be your minus charges here, and here will be the plus. Okay. So the drift business still continues going on. So you will see the same amount of drift as before. And that's happening because of the thermally generated carriers, minority carriers. Okay. So the I drift will probably be the same going from in the opposite direction. Okay. And as I said again, we introduce this forward bias voltage. Let's call it VF. VF is our forward bias voltage, and our barrier voltage will now change. The barrier voltage is here at the interface. That would change from V0 to V0 minus VF. Okay. And we will also see reduced depletion region width. All right. So this becomes very interesting now when you put all of it together. What's the interesting part? If you forward bias the diode, you will have current flowing from P to N, from positive terminal to the negative terminal. But if I reverse bias the diode, there will not be any current flowing. Okay. So the flow of current is unidirectional. It's only in one direction. It will not flow in both the directions. Okay. And we can model this part, this both diffusion and drift, with a very simple equation. Okay. I is equal to IS. I'm going to explain you all the terms. V divided by Vt minus Is. Okay. And this part is called diffusion current, and this is our drift current. Okay. And the model is, I am applying voltage V across the diode like this, and the current is flowing in this direction, I, and this is the model that we are talking about. I is equal to Is exponential V divided by Vt minus Is. V being the potential, V forward bias potential that we have applied in this case. Okay, so let's see how does this equation really fit into all the things that we have learned so far about the diode. Okay, before that, let me explain. Vt is called thermal voltage. And it's given by Kt over Q. K being the Boltzmann constant, T being the temperature in degrees Kelvin, and Q is the charge, Coulomb. For temperature, T is equal to, let's say, room temperature. We generally call it 300 degrees K. Vt is given by 26 millivolts. And we use this number quite a lot. So just keep that in mind. So you don't have to write Boltzmann constant, T, Q, all those numbers. If you know value of Vt at room temperature 300 K, then you can just use the proportionality and then figure out value at any different temperature. Let's go back to our equation here, the diode equation. and see if it's really doing what we think. Is it really modeling the whole phenomenon, the reverse bias and forward bias? Okay, so let's I is equal to Is exponential V divided by Vt minus 1. Okay, if V is negative, which means we are in reverse bias condition. Okay, so e to the power V divided by Vt will be much less than 1 because V is negative, and in that case your current I will be equal to minus Is, and that would be your saturation current, also called as SAT current, saturation current. So this makes sense. And under forward bias condition, your exponential V divided by Vt, if V is larger than Vt, then this is very large compared to 1. So we can simplify the diode current is equal to Is exponential V divided by Vt. So this would be your under forward bias condition. Okay. So the key part here is, as voltage keeps increasing, the current I will exponentially increase. Okay. Let's take a numerical example and then things will become very clear. Given that Is is equal to 2 10 to the power minus 16 amperes. As I said, Vt is equal to 26 millivolts at room temperature. And I'm going to numerically write down what would be the value for V and I. When V is equal to 26 millivolts, the current value will be 5.4 10 to the power minus 16 ampere. It's so small, so tiny. If we change this value to, let's say, 500 millivolts, okay, then still the current value is small. This will become 45 nanoamps. Nanoamps, 10 to the power minus 9. Now, if I just went from 500 to 700 millivolts, then this current increases to 98 microamps. From 700 to 750 millivolts, this increases exponentially now, 675 microamps. 750 to 800 millivolts, wow, this becomes 4600 microamps. And now from 800 millivolts to 850 millivolts, this becomes 32 milliamps, very large. Okay, so we call this process that our diode is turning on, turns on. And you can see around this value here, 700 to 750 millivolts, the diode really turns on. I want to give you a physical example of this diode. If you look at any buildings, right? For example, if you stay in a skyscraper, then generally what happens is on top of the building there is a tank, water tank, and generally there is a pipe that's pumping water, okay, into this water tank, and then that water tank is what is used to supply water to all of you. Okay. Now, if you think about this, if you keep pushing water from here, and whenever the water pressure drops, all the water will drain out, right? So they use something called NRV, no return valve. Okay. So this NRV looks like a very simple device, and I'm just going to draw it for you, and then it will be clear to you how this looks like a diode. Okay, so it has an edge like this, and there is a circular flap that it has, something like this, and the water flows from this direction and goes out this direction in this pipe. Okay, so this particular flap is held in place using a spring, which means if you are pushing water up, then it takes some effort for this flap to open up like this. Okay, but once you apply enough force of water from the bottom, the flap will open and the water will start flowing up. However, as soon as the water pressure at the bottom drops, the flap will come down and it will seal like this. Okay, so you will have this, and this is your ring, and then the flap will seal the place. So there is no water that can return back down. So our diode is kind of doing the same thing. When you apply a positive potential, it turns on. After a while, initially there is some resistance, and as soon as it reaches some critical voltage, the current starts flowing, the diode is in full operation. When you apply reverse bias, for example, for this NRV, if the water is going from the top to bottom, then it won't allow the water to flow out on the other side. Okay, so just wanted to give you a physical example, which is more of a mechanical or fluid dynamics type of example, which all of us are already using in our day-to-day life. Okay, so if we plot this current on like this, okay, so again I'm doing this, I'm applying positive minus, and then I'm applying it to a diode like this. This is V and this is current I. So we are plotting I on the y-axis and V on the x-axis. Why are we plotting I on the y-axis? Because V is what we are applying and I is the current that flows as a result of it. So when V is sufficiently small, sufficiently below certain value, for example, in this case, let's say we said maybe somewhere 700 millivolts, let's say. Okay, in this particular case, the current is quite small, and we kind of draw it this way. Let me use a different color. And even whenever the V is negative, we see reverse bias current flowing. Okay, and as soon as we approach this close to 700 millivolts, then we have this exponential effect with the current flowing, and then you will see something that looks like this. Okay, and this would be our forward bias condition, and this would be the reverse bias. Here the assumption is that I can apply a reverse bias to the diode as much as I can on the left side. So for example, I will not make notations here, just to show you. Okay, so what I am showing is something like this, and originally I showed you that, hey, the current is really small, close to zero, like this, and this is our voltage V and this is our current I. So in this case we are assuming that I can apply negative voltage or reverse bias potential for the diode as much as I can, but in reality that is not possible. So for example, if I am applying a positive and negative potential over here, okay, which is the high reverse bias, what will happen is you will have very high electric field in the diode, right? If you apply really large reverse bias voltage, then you will have really large electric field. And what happens as a result of high electric field? As a result of high electric field, you will have the structure inside this semiconductor will start breaking, the bonds will start breaking, okay, due to the high electric field. Now as soon as the bonds break, we have more carriers which are part of this electric field, and they will start flowing under the influence of this electric field. They will have really high speed because velocity is given by mu e, okay, for the charge carrier. So if electric field is really high, mu is the mobility, the velocity of the electrons will increase substantially, and under this condition they will start bumping into the atoms and they will start breaking more bonds, and then there will be more carriers. So all this action happens like an avalanche. If you have seen avalanche on Discovery or Nature TV, it's a small, like a ball of snow, which will which will start coming down, and along with it will carry a whole bunch of more snow, and then eventually the avalanche starts. So similarly, in this particular case, we will see an avalanche effect, and I'm going to show the avalanche effect with a different color. What you will see is something like this happening. Okay, and this would be your avalanche effect. Under extreme reverse bias. Okay, so this voltage at which this breakdown happens, this is called V breakdown, is really decided by the doping concentration in our P and N junction. So this voltage V breakdown is high when you have moderate doping concentration for P and N. Now we can take advantage of this effect. And if you remember at the beginning of the class, I showed you something called Zener diode. So if I increase the doping concentration, which is Na and Nd for my diode, okay, then this voltage breakdown, which could be 20 volts, I can bring it down substantially, and you would get something that looks like this. Okay, and this would be your Vz. So the avalanche is happening when there are moderate doping levels in the P and N junction, and we can intentionally increase the doping level in the diode to high doping level, and then we can reduce this breakdown voltage to V Zener, to lower voltage. Okay, so this V Zener generally is 3 to 8 volts type of range, and we can actually use this device to get a reference voltage between 3 to 8 volts, because this is something that will happen over and over again. Every time you put it to reverse bias, the current will flow. Now, key part you have to remember in both these effects is you have to limit the amount of current flowing through the diode. What I mean by that is, if you just take a diode like this, and if you apply a reverse bias potential like this, VR, okay, now this is a ideal voltage source. As soon as I take this reverse bias potential beyond certain value, there will be huge amount of current flowing in this diode in this direction. Okay, now that huge amount of uncontrollable current can burn the device out, because it's going to flow through really small area and it will burn the device out. Okay, and then the device is of no use. So what you generally do is you put in a resistor in the path somewhere. So you can put a resistor R. For example, if you are going to use this as a Zener diode, then you would like to put a resistor. What the resistor will do is it will limit the amount of current flowing through the diode, and the amount of current that will be flowing through the diode will be, you subtract the Zener. So for example, VR minus Vz divided by R. That would be the current that would flow through the diode. Another interesting thing we should talk about in the diode model is the following. Like this, and we are applying, I'm going to denote the values ID, and this is our cathode and this is our anode. Okay, and we are applying potential Vd like this. So as I said earlier, the drain current, the diode current is given by Is exponential V diode divided by Vt minus 1. As I've already mentioned, Vt is equal to Kt over Q, 26 millivolts at 300 degree K. Now what is this IS saturation current business? I'm going to explain you that. Okay. So let me explain it to you intuitively rather than writing a whole bunch of equations which you can review on your own looking at any device book. So this current IS is given by IS will increase if the area, the cross-section area of the diode is increased. So of course there is an A. IS has Q term in it. It has also Ni square and then dN divided by Na ln plus dP divided by Nd Lp. Okay, let me explain what this means. So A is area of the diode. Okay, and what is Ni? Ni is the intrinsic carrier concentration. Then when we talk about Na is acceptor doping concentration. Where does acceptor come into play? In the p-type part of the diode. Okay, and Nd would be your donor, and this would happen in the n-type. Okay. Now, what is Dn and Ln? Okay. So Dn and Ln are related to the diffusion aspect of the transport. So for example, Dn is called diffusion constant and Ln is the diffusion length. And the way to understand that, and similarly you have dP and Lp. For example, if you have really high n-type carriers on one side, and so across the junction it's going to start dropping like this and it will approach the final value here. Okay, so the diffusion constant describes this particular characteristic. Would it be this way? Would it be this way? That is described by Dn and Ln. Okay, and what is the diffusion length? So Dn and Ln would be for the n-type. Similarly, you will have dP and Lp for the p-type. Okay, so this is the way you can figure out what your saturation current IS of the diode is. Thank you.